When we talk about climb, we're going to talk about rate of climb and angle of climb. First, for the rate of climb equation, we have rate of climb is going to be power available minus power required over weight. And this is the generic equation where ROC is rate of climb, power available is PA, PR is power required, and W is weight. This is a generic equation. We also know this part, power available minus power required, is also known as excess power. Every time we have excess power, we can climb or go faster, but definitely climb. To draw the rate of climb curve versus velocity, we're going to draw it. So we have rate of climb, again, is power available minus power required over weight, and this is the generic equation. We'll talk about that with units, how it looks. If we draw that, this is versus velocity, it's going to look like something like this. Where the highest point on this curve, because this right here is rate of climb, that's going to be my max rate of climb, the highest point or best rate of climb, and the velocity that corresponds to that is going to be my Vy, where Vy is my best rate of climb or max rate of climb. And Vx is going to be my best or maxed angle of climb. And that's going to be a tangent. A tangent starting at 0. A tangent is, the definition of a tangent is a line that touches the curve only in one point. And that is going to be Vx. And this is at maximum gross weight, sea level standard conditions. Okay, now if those conditions change, then Vx and Vy are going to change. Vy is going to decrease with altitude, and Vx is going to increase with altitude, and I'll show you why. At a higher altitude, my excess power is going to be different. So let's say this black curve was at sea level standard condition, let's say at 5,000 feet, say at 5,000 feet of altitude, then my excess power is going to be less. Why? Because the density is lower and the airplane is going to perform worse. The new Vy is going to be the highest point right here. So this is going to be Vy at 5K, that is going to be less. And Vx is going to be a bit higher. So this is going to be my Vx at 5K. And at 10K, so let's draw it in a different color. Right here, my excess power is going to be even less. So let's say at 10,000 feet, Vy right here is going to keep decreasing. So this is going to be Vy at 10K, and Vx is going to be a bit higher. So this is going to be Vx at 10K. So if we draw a graph that shows velocity versus altitude, Vy is going to be higher than Vx at sea level. So this is going to be Vy, this is going to be Vx, it's going to be lower at sea level. But as we increase in altitude, Vx is going to increase, Vy is going to decrease, and the point where they intersect is called the absolute ceiling. So when we talk about climb and the examples and the formulas, we have rate of climb is power available minus power required over weight, okay? Or we can put it in terms of thrust and velocity, knowing that power is thrust times velocity. We can write in terms of thrust and velocity. So power available is thrust available times velocity minus power required, that is thrust required times velocity over weight. We know that thrust required is the same as drag, and we can take velocity out because it's in both, because it's a common to both. So we can say velocity times thrust available minus thrust required over weight. Very good. So now if we're trying to do the calculations and we want the rate of climb in feet per minute, there's going to be a unit conversion number that is going to be 33,000, and that's so we get rate of climb in feet per minute, and we have power available in horsepower minus power required also in horsepower over weight in pounds. So that is the unit conversion number. This 33,000 is the unit conversion number to convert to use power and horsepower and then get rate of climb in feet per minute. We can also do it in terms of thrust and velocity if what we have is thrust, and then our unit conversion number is going to be, again, rate of climb in feet per minute is going to be 101.3 times velocity times thrust available in pounds minus thrust required in pounds over weight in pounds, and this velocity is in knots, and that's why we have this unit conversion number. And last but not least, so this is going to be for rate of climb. And then we have angle of climb. That is going to be sine to the -1 of thrust available minus thrust required over weight. And this is going to be in pounds. Thrust is going to be in pounds and weight is going to be in pounds. So this angle of climb is going to be in degrees. And make sure that you have your calculator in degrees when you do the sine to the -1. Okay, so we can do an example. If we have weight equals 84,000 pounds and thrust available equals 15,600 pounds. Velocity is 195 knots and drag at 195 knots is 2,200 pounds. Remember that drag is the same as thrust required. So we want to find the angle of climb and rate of climb. So angle of climb, again, is sine to the -1 of thrust available minus thrust required over weight. So it's going to be sine to the -1 of 15,600 minus 2,200 over 84,000, and that is going to be 9.18 degrees. And now for the rate of climb, it's going to be 101.3. Why? Because we have everything in terms of thrust instead of power. 101.3 times the velocity times thrust available minus thrust required over weight, and that is going to be 101.3 times 195 knots times 15,600 minus 2,200. Where am I here? Over 84,000. And that is going to be 3,151.15 feet per minute. When we look at the generic equations, again, this one is without the unit conversion number. When we look at the generic equations, we see that the rate of climb is dependent on the excess power, and the angle of climb is going to depend on the excess thrust. So if, for example, we have, let's say for a jet, let's say we have thrust required that is the same as drag, and this is a jet because my thrust available is constant for a jet, and we have this is thrust and this is velocity. I can find the point of Vx, my best angle of climb is going to be where I have the biggest excess thrust. So the place where my thrust available and thrust required curves are farthest apart, that is going to be my Vx, where thrust available and thrust required are furthest apart. And for Vy, I'm going to look for the maximum excess power. So where I'm going to have, so this is not thrust anymore, this is power required. And let's say for my prop, power available is roughly constant for my prop. The point where power available and power required are farthest apart is going to be my Vy. So right here is going to be Vy, where power available and power required are furthest apart.